Here we are again. The textbook for both logic courses is Logic for Computer Science, Classical and Non-Classical, Springer 2019, and I'm the author. So now we are already in the last chapter, chapter 11, which is Formal Theories and Gödel Theorems. And here we go. The plan is, first, we define formal theories. Part 2, we will define the formal theory of natural numbers. And then we will talk about consistency, completeness of theories, and Gödel theorems. And then we will finish with the proof of Gödel incompleteness theorems. There are 2 of them. So, formal theories. Formal theories play a crucial role in mathematics, of course. Historically, they are defined for predicate logic and also other first or higher order logics, classical and non-classical. We deal now with classical predicate logic and theories based on classical predicate logic. And the idea of formalism in mathematics, from which the idea of the concept of formal theories appeared, came from Hilbert program, and so they were developed in connection with Hilbert program. Hilbert program, I already said, but Hilbert program was developed by Hilbert by the beginning of 20th century as the program for mathematics for the new century, and we still I'm almost done developing all of the Hilbert problems. So one of the objectives of Hilbert was to construct a formal theory that would cover whole mathematics, and then to prove consistency of mathematics applying the simplest of logical means. And roughly, we say that theory, mathematical theory, and then a formal theory is consistent if we cannot have a formal proof in it of a formula and negation. I will write it here because this is not so. Theory, formal, F for formal, is consistent if and only if no proof of A and not A. So this is which is, of course, if you prove a formula and negation, you have inconsistency. And that's what was stated by Hilbert, and he wanted to have it for the whole mathematics. In 1930, Hilbert stated his problem in 1905. In 1930, still in his 20s, Kurt Gödel made a historic pronouncement that Hilbert consistency program could not be carried out. He justified his claim by proving what is called inconsistency theorem. And also it's called also second incompleteness theorem. I'm going to talk about it. So roughly speaking, he proved, and that is our goal today, to explain at least and carry his proof of inconsistency theorem and incompleteness theorem. Of course, to do it in full-fledged details, it takes the whole book. But you'll see that we can understand and we can do the most important parts and I hope I will make you understand what it is and how you prove it. So, roughly speaking, a proof of the consistency of every formal theory that contains arithmetic of natural numbers can be carried only in mathematical theory, which is more comprehensible than the one whose consistency is to be proved. And so the minimal, somehow what he wanted to prove is arithmetic of natural numbers. So to prove of consistency of formal, elementary, first order arithmetic of natural numbers can be carried only in mathematical theory, which contains the whole arithmetic, but also other theorems that do not belong in arithmetic. It means you cannot prove consistency of arithmetic using means and formal proofs and the language only of arithmetic alone. And then it applies to formal theory that would cover the whole mathematics, because it would obviously contain arithmetic of natural numbers. So, and that means that Hilbert consistency program fails. It is extremely important thing, because what happened that instead of looking at the direct proof of inconsistency of mathematical theories, mathematicians concentrate largely on relative proofs. So you can say that you prove consistency of one theory if the other theory is consistent, etc. Those relative proofs are rooted deep in conviction that even though it cannot be proved that the theory of natural numbers is free of inconsistency, is consistent. The next important notion is the notion of completeness of the theory. It's a different notion than completeness of logic. So we have a theory. We say that theory is complete if every sentence, it means formula without free variables, of the language of the theory. Remember I said the language, everything happens in the language of the theory. There is a formal proof in the theory of a formula or of its negation. So I write it here. Theory is complete. Now, the notion of completeness, if for any sentence A, of course, of language of the theory, there is a proof of A or of negation of A. So it means completeness means the full information. It means it's complete. Whatever you state as a sentence of the theory, you are sure that you can have a proof or a proof of negation of that theory. It's a very strong property, because completeness in this sense is completeness about proving anything you state or proving the negation of the state. If mathematics was complete and we had Fermat theorem, you would know from the beginning that Fermat theorem has a proof or negation of Fermat theorem has a proof. That's why it was open for so many years until the proof was found. Okay, so from that, so this is complete theory. From that, if you negate this, you have incomplete theory. So theory is incomplete if there is a sentence, for any sentence, if there is a sentence A such that, you negate that, no proof of A and no proof of not A. So neither A or not A are provable. Neither A nor not A, there is a sentence, is probable. So such sentences which neither A nor negation is probable are called undecidable or independent sentences. So it might seem that we should be able to formalize natural numbers in such a way that it would be complete. It means any statement in the theory of natural numbers, means about the natural numbers, is free of this kind of sentences. It means whatever you formulate in natural numbers, you can prove it or disapprove it. And Gödel, and we are going to prove today, proved the incompleteness theorem, because we have incompleteness, every consistent formal theory which contains arithmetic of natural numbers is incomplete. So you always can find independent sentences, and the proof is to find those independent sentences, and that's we'll talk about it. So now, inconsistency theorem follows from incompleteness theorem. So that's why we call Gödel first incompleteness theorem and second incompleteness theorem. The renaming those inconsistency theorem and incompleteness theorem as the two incompletenesses theorem is because it's very if somebody does not understand what inconsistency means, it is misleading. That it doesn't mean that arithmetic is inconsistent. So the third part of Hilbert program posed and was concerned about the problem of decidability. So we know the formal theory is decidable if there is a method determining for infinite number of steps whether given formula of the theory is theorem of not. And most of mathematical theories are undecidable, and Gödel proved in 1931 that arithmetic of natural numbers is undecidable, formal arithmetic of natural numbers. So now we have to define quickly the formal theory based on predicate, first order language. So formal theories are also called first order elementary theories or formal axiomatic theories. They are stricter, and you will see in a minute, than the theories we use in the whole mathematics. So we considered formal theories based on complete classical Hilbert-style proof system. We have a predicate base. L is a predicate logic where P, F, C are infinitely enumerable, and formal theory based on the proof system. We get the formal theory based on the complete proof system by adding special axioms called specific axioms when we define in general way what the specific axioms are. So specific axioms are certain set of formulas of the language of our system, which are classical tautology, which are not tautology of the language. So they are called specific axioms. That's exactly what we defined before. So they are called specific axioms. So specific axioms are characteristic description of the universe of the formal theory, and they are only true in certain structures as opposed to tautologies, which are always true. So now the next important notion, because all those theorems and all these notions are defined for the language of the formal theory. So formal language theory, how we get the formal language of the formal theory, is determined by the specific axioms. So we restrict all our sets of FPC, predicate, functional, and constant symbol, to predicate, functional, and constant symbol appearing only in the set of specific axioms. And of course, they have the same propositional connectives. So the formal theory is now a proof system which these are logical axioms and these are specific axioms, and the language of formal theory is determined by the set of specific axioms, is called the language of the formal theory. And now we have given a formal theory. We denote by FSA the set of formulas of the language of the theory, and by T, we denote the set of all probable formulas in T. And we write that B has a proof in the theory T if B has the proof from the set of specific axioms. Now, I use here fat capital T as the set of all probable statements in the theory T, and I use that notation. T is a formal theory, and fat T is now the set of probable, because that's how it is usually, notation is used in the literature which I refer you to. And so now, a proof system is called logic with equality, LE, if and only if the language L contains as one of its predicates a two-argument predicate, which we denote by equality, such that we have the axioms of equality. Now, so it has all other, it's infinite, it can contain infinite number of all other functional predicate and constant symbols, but it must contain a special one, which we call equality, and that's why we use the special symbols, which is equality. And now you have the axioms, where T alpha is the set of terms of the language, and I have the axioms are for the variables, so U equal U. If U equal V, then V equal U. So these are natural axioms of equality. And now, if you have relational symbols, so if all variables are equal, if this variable is equal that, so whatever you put the relational symbols on them implies the relational symbols of that. So these are all true in our universe. And the Hilbert proof system, defined in chapter 9, is logic with equality with the set of specific axioms. So the logic with equality, specific axioms are empty, because these are just everything happens within our Hilbert-style logic system. And formal theories are abstract models of real mathematical theories, but they are like sort of smaller pieces of the real formalization of the bigger mathematics. And that's why we call them elementary theories. For example, we can call theory of equality, which is different than logic with equality. The language would be propositional connectives. You have one predicate, functional are empty, constants are empty. This is two-argument predicate, and we intended interpretation of that predicate is equality, so we use equal instead of writing P. Intended interpretation, we use it all the time, this word. Really, this is the word for artificial intelligence. We use the word intended interpretation because we want to describe whatever exactly we want in the given universe. So intended interpretation of this symbol P is equality, and we will use it just because that is equality. Intended interpretation, once we do the interpretation and models, would be the real equality which we want to be, and you have specific axiom of equality. And also we choose to write those specific axioms as open formulas. Sometimes it's more convenient to write it as the closed formulas. And so if we want to, like, you just close all these open formulas, and we put the universal quantifier in front of that, so that you have sentences, right? So these are all sentences. And now, for example, the theory of partial order, what it would be, partial order, you have equality, and you have two predicates. Functions are empty, constants are empty, and again, one predicate is equality, and the other intended interpretation is a partial order, and normal symbol is less equal, so we write that the language is equality less equal, and then we write the axioms, which are specific axioms. Have two groups. One is equality axioms, and then you add our partial order axioms, which we know, which is reflexivity, antisymmetry, and transitivity, and you can also make sentences out of it. And the model is called partially ordered structure. And theory of partial order is the language, and you can also, like, for example, there is another formalization of partial order. So this is the same, that where you have only P, and you write symbol less, and we write that X is not less than Y if negation of X less than Y. So it means it's not true. It's not true that that relation holds between X and Y, and we can now, specific axiom would be only two axioms, but this is still the same theory of partial order. Linear order, we add another axiom. It means that which means that any two elements are comparable, so X is less equal Y, or Y is less equal. Now, dense order, you have the axiom of density, our classical axiom of density. Lattice theory, if you want to have a formal lattice theory, you have functions. Now, you have language, let's do here. You have two functional symbols, which is and lattice intersection and lattice union, which are atomic formulas of our language. And the language would be, you have equality, you have less equal, and functions, our operation, lattice operations are functions of union and intersection, corresponding, and then you have equality axioms. You have and you have all logic with equality, and we add axioms for the and intersection and connection with the intersection and less equal, and the same you have the characterization of intersection and or. So, and then that symbol is the set intersection, and this is, we write here, this is a conjunction, and that is set intersection in the language of theory. So this is a logical connective, and that is set. That's why we use two different symbols. So that is intersection of sets, and that is union of sets, and this is a conjunction because we use that symbol of conjunction in our propositional language. And then you have some other examples: partial order axiom, lattice axioms, distributive lattices, theory, formal theory of Boolean algebra. You have now again equality or partial order symbol, intersection, set intersection, and set union, complementation, and empty set, and you have axioms of Boolean algebra. Theory of groups, again, in theory of groups, we have two functional symbols. One, of course, P is equality, and intended interpretation of F is a group operation, and intended operation of another symbol is the inverse operation. So we write the language is in intended interpretation, you have equality, you have group operation, and inverse, and constant is the union, the unit of the group, and then you have the specific axioms would be equality axioms, plus you have how it behaves, equality, if x equal y and y equals z, that y x equals z, so that is your transitivity. And then if x equal y, then the inverse of x equal inverse of y, and so on. So you have the group axioms. And then if you have, you add the x or y equal y or x, so it's called abelian groups. And you can, but these are, observe that elementary theory, all we want to prove in elementary theory is formal proofs, like in pure logic. So they represent only a small fragment of corresponding axiomatic theories as we use it in mathematics. For example, the group theory, lattices, Boolean algebra theories, and other theories are often the fields of mathematics, and they are much, much richer. So that's why we distinguish the formal theories from mathematical theories, which you can formalize in the larger language of set theory and so on. So the theorems developed in axiomatic theories in mathematics, like, for example, representation theorem of Boolean algebra, which we talked before, cannot even be expressed, not to mention proved, in the language in respective formal theories. So mathematics, you need a larger language, and then there are formal theories in much larger language. So, for example, elementary group theory, we distinguish elementary group theory from the group theory as we do it in mathematics. So now we are talking in piano arithmetic. It means the formal theory of natural numbers. Because if you want to prove something, we need to have a formal proof. We need to be in full-fledged formalism. So piano arithmetic, we have natural postulates, which was accepted, and Peano was first who postulated it. For example, 1, 0 is a natural number. if n is natural number, there's another number which we denote prime and call successor of n. So intuitive meaning of n prime is n plus 1. Now, that 0 is not n prime for any natural number. So this is, you have your first is 0, it's not successor of any number. And then if you have two successor, then the numbers are the same. So it means we can think about it. If n plus 1 equal m plus 1, then n equal m for all natural numbers. And we say if V is a property that may or may not hold for natural numbers, and you have property if 0 has this property, and whenever a natural number n has that property, then n prime, it means n plus 1, has the property, then all natural numbers have property. That's what we call the principle of mathematical induction. So Peano postulates, he's stated like that. We have to formalize it, and I will give you the formal axioms in the proper language, together with certain amount of set theory are sufficient to develop not only theory normal of natural numbers, but also theory of rational and real numbers. But you need extra that what we are going to define as an axiom. But Peano postulate counteract as a full formal theory, as they include intuitive notions as property has property. So if to have a formal theory, you have to say what is property and so on. So we present here formalization by Mendelssohn. He did it in 1973, and it is included in the smallest detail. So I refer to his book, Introduction to Mathematical Logic, which is a beautiful book. And we refer you and readers and students if you want to have, and I will show some formal proofs which are total formalization of some Mendelssohn proofs. So we assume now that Peano arithmetic, which we're going to define, is based on a complete Hilbert's type proof system of predicate logic with all P, F, C, etc. So we have this, we know that we have as a base, we have complete Hilbert's type proof system. Whatever it is, but we have a complete proof system. Additionally, we add new axiom, which is co-generalization rule. We do so to facilitate use of Mendelssohn book as supplementary reading. So we have whatever we had the complete proof system, and chapter 9 we did that complete proof system with the equality, with all the axioms, but we add the generalization rule, which is very useful rule. And now, formal Peano arithmetic is the language. You have all our connectives, you have equality, you have successor, you have two argument function, three functions, that plus, which corresponds to addition. So we use intended interpretation. We keep plus for successor, and we use dot for multiplication, because we deal with intended interpretation. So, and now we have axioms of Peano arithmetic. This is a formal Peano arithmetic, and they are pretty intuitive. Like, for example, 0, which is a special constant, is not successor of x prime for any x prime. If 2 are x prime equal y prime, etc., x plus 0 is x plus y prime successor of y is x plus y successor, and so on. So they are very intuitive axioms, and that is as close as we can have to mathematical induction. It means for any formula of the language of the theory, so A is a formula of the language of the theory, if A0 implies for each x, ax, then implies x prime, so from n to n plus 1, then for all x, ax. So that is a formalization of mathematical induction. So the axiom is called principle of mathematical induction. It does not fully correspond to postulate, Peano postulate P5, but refers intuitively to all possible properties of natural numbers. The axiom P1, P9 of Peano arithmetic are particular formulas of the language, right? We know our language, we defined it exactly. And the axiom is called axiom schema because provided in infinite number of axioms, right? Because it's for any formula, the axiom says, you see, that holds, this is for any formula. So these are variables, and that is for any formula. So this is this axiom schema for any formula of the language of Peano arithmetic. So so in fact, you have one axiom, but it represents infinitely many statements. So we have an important theorem, which is called Rylnar-Zewski theorem. You can see there's always poles there somewhere, that Peano is not finitely axiomatizable. So that there is no theory K having only a finite number of proper axioms whose theorems are the same as Peano arithmetic. So that is an important theorem. And we say that the theory T such that theory is Peano arithmetic, it means the set of all theorems of theory T. That means theory T, now phat T is the set of all probable statements in the theory T, and PA is the set of all probable statements in Peano arithmetic. So any theory such that everything which you prove in that theory, you can prove in Peano arithmetic and vice versa. It's called Peano arithmetic. So it means you can have different axiomatizations, but you call it still Peano arithmetic. And of course, when we have, we can have closed Peano arithmetic. If we like to have, we put, we close, we put the sentences. Each statement we put we quantify. So this is called the closed sentences. So this is called the closed Peano arithmetic, and of course this is the same as it was before. And for example, we prove that if you quantify everything, we can prove that all the theorems of closed Peano arithmetic is the same as Peano arithmetic. And here's a little proof, formal proof. And also the formal proof, you see, these are formal proofs that we can B1, B2, B3, you have this, and then you do the generalization rule from this axiom. Then this is your Peano arithmetic axiom. Then I do generalization rule. Then I do generalization rule. Then I do generalization rule. So for first axioms, and then I obtain at the end the C1 axiom, and you do the same for all the axioms. and you construct a really formal proof. Now and then you prove another axiom, so that's what it means. That, and then this is a little bit the completeness. By completeness of S, we know that, for example, this is a predicate tautology, so it's provable in our proof system for any formula AX. So AX is particular sublanguage of piano arithmetic. So if you have AX of that form, so then you can close it and do whatever. So you can construct a formal proofs. See, now we construct a formal proof B1, B2, B7 of P1. It is P1 in piano arithmetic in closed piano arithmetic as follows, and I put it. I'm showing you this to show that if we prove for everything what we prove, we can construct a formal proofs, and then you can play with other axioms. And now we have some basic facts about piano arithmetic, which are very intuitive. Like, for example, we had only the axioms were not for terms, but for variables. So we can see that you can have not only variables, but also for any terms. So the following formulas now are generalization of the axioms for any terms. And again, we have to prove each single one by you constructing a formal proofs. So, and when you go slowly, you can see that you have all details how you construct the formal proofs. And then you have, for example, the same, you can construct the formal proofs from piano arithmetic for all these properties now for all terms. And then you go on. So, for example, here you construct a formal proof B1, B2, B3, B4. I always find some typos. 3, not 34, it's 4. And of T equal T. You see, I want to prove T equal T, and now I construct the formal proof of T equal T. This we have a formal proof. Here you have a formal proof that if term T equal R, then R equal T, and again you construct the formal proof. You can use a tautology, you can use the previous facts, etc., modus ponens, and the rules of inference which we need. So, and then you go one by one, and you can see that constructing this, we often use the already tautology because our basic proof system, all piano arithmetic is always based on complete proof systems. So you can put, if you need certain tautology, and you can see it's tautology. This is T equal S, R equal T, R equal S. You can rewrite it, which tautology it is. So you use the tautologies. And then, for example, this we prove by principle of mathematical induction. And here's a nice proof step by step. It's a lot of work, but you can prove all these properties. So I'm just showing you, you have to go step by step, and I did all this. Like, for example, we prove that the following formulas are provable in piano arithmetic. You have distributivity, you have associativity, cancellation, and so on. And those proofs, they are all not in such detail. They are stated or given without proofs in Mendelssohn book. So I put all these formal proofs as a nice exercise for you to see how it works, and also to install in you the fact that now in formal theories we construct the formal proofs as we did in pure logic. So now, natural numbers, we need numbers, right? So, and if we want to talk, we want to introduce the numbers. So the numbers in the formal Peano arithmetic are called numerals. And numeral, 0, is a constant. Remember, 0 is just a constant. We intended interpretation is 0. And then you can form 0 prime, 0, 0, and they are called numerals, and you denote them like with bar. So 0 is a constant, and 0 bar is the notation of number 0. 1, 0, next after 0 is 1. 0 successor would be 2, 3 successor is 3, and so on. So the term this is number 0. This in natural interpretation for any natural number, n plus 1 bar. Numeral is n numeral successor, and n stands for corresponding numerals, and so on. So now we can talk about numerals. And numerals are defined recursively. Recursively, 0 is a numeral, u is a numeral, u prime is also numeral. So you have some, now we can like sort of talk about numbers within Peano arithmetic. So for example, t plus 1 is t prime next. So now we have that what we wanted, that n plus 1 is n successor. And you have, and again, you have now the proper language, and you can prove all this. You can construct now the formal proofs of all these properties, right? And we, for example, here I give you a formal proof of this, and we apply a mathematical induction, and you construct the formal proof. And now you can prove that, for example, for any natural numbers, if n not equal m, then numerals are different. If you have natural numbers, that numerals are different. And any model, of course, and we prove that any model of Peano arithmetic is infinite. And also we can introduce order relation. We can, so once you introduce order relation, you can construct formal proofs of properties. And here you have our 5 properties. And now you can have, and you use, and then you can talk about several stronger forms of principle of mathematical induction. For example, this is called complete induction principle, that for any x z, if z is less than x, because now I have this order defined in our Peano arithmetic, then a z, then if this implies ax, then for all x, ax. So that is provable in Peano arithmetic. So you can prove that you can have a complete induction principle in Peano arithmetic. And again, I refer to the Mendelssohn book, and I found that book the most rigorous and complete. And even the proofs which I included here are even more detailed version. So Mendelssohn is the most detailed version I ever found, but then I gave you more detailed proofs that in Mendelssohn, which is easy, of course, to do as an exercise. So that is, everything is called, okay, from this point, one can generally translate onto the language of Peano arithmetic and prove in Peano arithmetic the results from any textbook of elementary number theory. So when you have what's called elementary number theory, you can retranslate it as we did step by step, just in the language of piano arithmetic. And we know that piano arithmetic is not finitely axiomatizable. So the question is, for example, can we have piano arithmetic which is finitely axiomatizable? And it is yes. The answer is yes. And it is Robinson RR piano arithmetic is Robinson, piano arithmetic is RR. And it means that we have a sub-theory of piano arithmetic which is finally axiomatizable, and it is the same expressive power with respect to Gödel theorems as discussed, and we will prove in the next section. So, for example, Robinson arithmetic, you have language is the same as piano arithmetic, you can see, and you have 14 axioms. And there's no induction. It's like sort of hidden. So this is a finite axiomatization of piano. So it's called Robinson arithmetic. And Gödel showed in his famous incompleteness theorem that there are closed formulas. Now we are called closed formula sentences of the language of piano arithmetic that are the probable or disprobable in piano arithmetic, if piano arithmetic is consistent. So that is, there is a sentence such that sentence now of piano arithmetic, you see, so now incomplete, of the language of piano arithmetic. So now we have those axioms, we have the formal theory, and Gödel showed the incompleteness theorem. Gödel is that there is a sentence, it means now closed formulas of the language, sentence of the language of that little language which we defined in piano arithmetic, that in piano arithmetic, neither this sentence nor negation is probable. If, you see, if piano arithmetic is consistent. So that is, we wanted to have it in completeness in general. It can be done if piano arithmetic is consistent. And that is Gödel incompleteness theorem. So you know, and you will see the genius of Gödel was to find that sentence. There is, you see, there is a sentence. What does it mean? There is a sentence. It means you have to have that sentence in the language of piano arithmetic. So you have that language. What is the sentence? And that is the goal, to show you that sentence after Gödel. So also, Gödel incompleteness theorem also says that there is a formula that is true under standard interpretation, but is not probable in piano arithmetic. So standard interpretation, it means those numerals and primes and plus and minus are what we understand as normal standard arithmetic of natural numbers. So Robinson proved in 1950 that Gödel theorems hold in his system, and that RR has the same incompleteness properties that piano. Remember, piano arithmetic was not finitely axiomatizable. So that is a very strong result, that you can repeat all Gödel just that big book, techniques for his finitely axiomatizable version of Peano arithmetic. Beautiful theorem. So now we go to formalization of Gödel theorems and the proof of incompleteness. The answers to Hilbert problem of consistency, completeness of formal theories were given by Gödel in the form of two theorems. There are some of important and of his two theorems which we discuss. There are some of the most important influential results of 20th century mathematics. And here are two definitions, formal definitions of consistency, semantical and syntactical. Semantical definition is based on the notion of a model, and we did it in previous chapters. A theory is consistent if the set of specific axioms has a model. So it connects consistent, and syntactical definition says that theory is consistent if one can't prove contradiction. So consistency, and that we use this, right? We say it's consistent, which we cannot prove contradiction. It means a formula and negation. And model, if you use the model, it means the truth. It means semantics. We say that theory is consistent if the set of specific axioms has a model. And we use the syntactical definition in chapter 5 in the proof of completeness theorem for propositional logic, and in chapter 9 for predicate logic. And now we can extend this propositional definition to predicate language and so on. And so when we have model for a theory, we have a theory, and we say the structure is a model for the set of specific axiom is called the model of the theory. So structure is a model for the theory if it's a model for set of specific axioms. So the first model consistent theory is a first order theory, is model consistent if and only if it has a model. It means specific axioms have a model. And so Peano arithmetic, we have a structure and such that universe is natural numbers, and interpretation is natural interpretation. Constant 0 is a natural number 0. The function symbol is a successor. So successor n is n plus 1. And we have two argument functions, multiplication and addition. And predicate symbol equality is interpreted as inequality relation in natural numbers in the structure. And that what we have is called the standard model of Peano arithmetic, is a model structure, natural numbers, the real equality, successor, plus, and it's called a standard model of Peano arithmetic, and I is called standard interpretation. And any model of Peano arithmetic in predicate equality is interpreted as equality in natural numbers that is not isomorphic to the standard model is called non-standard model of Peano arithmetic, and you have so all the theory of non-standard models of Peano arithmetic, etc. But, and also, of course, if we recognize that the set n of natural numbers with standard interpretation, it means our structure M to be model of Peano arithmetic, so Peano arithmetic is consistent. However, semantic methods giving the amount of set theoretical reasoning are regarded by many, and were such regarded by Gödel, as too precocious to serve as a basis of consistency proof. So, so in a sense, we have not proved formally that axioms of Peano arithmetic are true under standard interpretation. We just take it as obviously true because we build it everything in that intuition. So for this and other reasons, it is common practice to take the model consistency of Peano arithmetic as an explicit and unproved assumption, and to adopt it after Gödel, the following syntactic definition of consistency. So that's why Gödel introduced the syntactic, it means probability of consistency. So it means theory is consistent if there only if there is no formula of the language of the theory such that you can prove formula and negation. And of course, in consistency, there is a formula that you can prove. And here are the basic characterization of consistent theory. A theory T based on the complete proof system, remember we always base those theories of complete, is consistent if, only if, there is a formula A of the language which does not have a proof. And here it's very it's useful to use, and we discussed it already in previously, those notions, syntactical notion of consistency, because this also sometimes is used as definition of consistency if the language does not have negation. Because in classical logic, you have your language has negation, so you can talk of formula and negation of formula. But if the language you have a logic on which the whole theory is based does not have negation, you can still have the notion of consistency, and that is often taken as the definition of consistency of the theory. And then I prove you very nicely, which uses, for example, different tautologies. Now, T is probable in the theory, but it is a tautology, so all tautologies are probable in our theory. So you have certain tautologies, and you use them, and then you construct the proof that of our theorem, the theory is consistent if and only if there is a formula which does not belong to the language. And then, as I said, that sometimes it is used as the definition of the theory. So the next important characterization of formal theory T is one of completeness, and we discussed that, and here's the formal definition, which here was stated more in English. So now in our formally, you say exactly the same. Theory is complete if and only if, for any closed formula sentence of the language, A can be proven in the theory or negation can be proved in the theory, and incomplete, etc. And any sentence with that property in completeness theorem is called independent sentence or decidable sentence. The incompleteness definition says that in order to prove that a given theory is incomplete, we have to construct a sentence of the language of the theory and prove that neither A, where it is, neither A nor negation of A is probable. So now we are almost ready to discuss Gödel theorems. I discussed a little bit because I said that we are doing it for Peano arithmetic. So one of the most comprehensive development and proofs of Gödel theorems can be found in Mendelssohn book. It's a really, but it's over 50 pages long. Beautiful, technically sound, and really, really very well carried. We will do it. But we present a short and high-level approach adopting the style of Zboryński chapter in Handbook of Mathematical Logic, Studies in Logic and Foundation of Mathematics. It's a handbook, you can Google, it's for free now, and it's everywhere. The chapter is over 40 pages long, and what seems to be norm when want to prove Gödel theorems. But Zmorinsky chapter is again written in a very condensed and general way and concentrate on presentation of modern results. So I want to present that version. And also, we want to bring to attention the introduction to Zmorinsky chapter, which contains excellent discussion of Hilbert program and its relationship to Gödel results. So the chapter also provides explanation why and how devastating Gödel theorems were to the optimists reflected in Hilbert consistency and conservation programs. Hilbert believed that we can prove consistency of the whole mathematics and so on. So that was really this beautiful chapter. So here I have slides, and I'm just only say at the beginning. So Hilbert proposed conservation and consistency program to respond to Brouwer and Weil propagation of the theory that existed on Zermelo paradoxes free axiomatization of said theory makes the need for investigation into consistency of mathematics superfluous. And that, remember Brouwer started intuitionistic logic and so on. So Hilbert wrote, Brouwer and Weil, would chop and mangle the science. It would follow, if we follow such a reform as the one they suggest, we would run the risk of losing a great part of our most valuable treasures. Beautiful language. And he stated his conservation program as follows, I'm reading. To justify the use of abstract techniques, it means logic, he would show by as simple and concrete means as possible that the use of abstract techniques was conservative. It means that that any concrete assertion one could derive by the means of abstract techniques, formal theories, logic, one would derive without them. And now I explain the Zmorinsky clarification and the whole jargon. It's a beautiful way he did it. And here, what is phonistic proofs, computation, how you refute Weil and Brouwer, Hilbert, and to refute Weil and Brouwer, Hilbert required his conservation property to be statistically probable, and then he formed the consistency program and so on. And so I am not I'm leaving this for you to read because we want to get to the Gödel theorems. But before I leave you here, what is important that is the notion of encoding. And the notions, what is the encoding? So that we have, if we have a real statement, for example, for all x f x equals gx, a, and we prove a, then there is a derivation d of a in the theory I. Is ideal system. So, but the derivation a concrete object, and for some real formula encoding derivation in I, you see this is formula which encode derivation in I. So that means A is some code for I. So that's why we will encode statements, introduce encoding of a statements whatever from Peano arithmetic in Peano arithmetic. So that is a code for A, and so on, and how you do the encoding. So to prove consistency, you have to prove such a formula that not P derivation of A and you have a derivation of not A, and to make that rigorous, you has to define, explain basis of encoding, develop assumption of the formula, deliver argument in a rigorous way. So the whole idea is to make the above argument rigorous. One also have to develop in a rigorous way the whole apparatus developed originally by Gödel, which is needed for the proofs of his theorems. So, and we bring it here because at this stage, because above argument was clearly invited Hilbert to establish his consistency program. And so and Gödel proved that his consistency program couldn't work. So now we have Gödel incompleteness theorems. In 1920, I repeat it because it's such a strong statement. He was 20. Announced that consistency program could not be carried, right? And he stated his two theorems. First, incompleteness theorem, that let T be a formal theory containing arithmetic, then there is a sentence A of the language of that theory which asserts its own unprovability, and such that if T is consistent, then you cannot prove A, and if T is omega consistent, which is a new notion, then you cannot prove not A. So you see here what I say, there is a sentence of Peano arithmetic, but he does it in more general way, that you have A is a sentence. A is you have a formal theory that contains arithmetic. There is a Peano arithmetic, there is a sentence of the language of the theory, and this sentence asserts its own unprovability. So that, and what does it mean in the formal way, I will explain, and such that exactly what we have, that if theory is consistent, you have the sentence, if Peano arithmetic, so here is if theory is any theory which contains Peano arithmetic, if theory is consistent, then you cannot prove A, and if it's omega consistent, this is stronger, then you cannot prove not A. So this is called incompleteness theorem. And second, incompleteness, which was used to be called inconsistency theorem, that if our theory is consistent, so still our theory contains arithmetic, if it is consistent, then such sentence, not probability, is a sentence con T, where con T is the sentence in the language, because everything is back, has to happen in the language of the theory. This is a sentence which asserts the consistency. And of course, we have to develop all machinery to be able to formulate that consistency. And of course, second incompleteness theorem destroys consistency program, right? It states that R cannot prove its own consistency, so obviously it can't prove consistency of I. This R and I was ideal system and formal system. So Smorinsky's argument that first incompleteness theorem destroys the conservation program is as follows. If Gödel's sentence A is real, because you have those real and it is easy seen to be true, it asserts its own unprovability and is indeed unprovable. Thus, the conservation program cannot be carried out, and hence for some must hold The same must hold for consistency program. And now you have, of course, once that is Zmoriński, and that in Sen, in appendix of his book Hilbert Program, an essay on mathematical instrumentalism in Springer 2012. I bring everything to our today day. He argues that Zmoriński argument is ambiguous, as he doesn't tell us whether it is a probability in R and a probability in I and so on. So discussion still holds on. So anyway, I recommend readers or students interested in philosophical discussion of Hilbert program to read this appendix. It's very interesting. But we will follow formulating completeness theorem in more precise way. That's our goal. So arithmetization and encoding. In order to formalize the theorems in formal way, one has first to translate the Gödel sentences A and consistency T into the language of the theory. For the first incompleteness theorem, one needs to translate, it means as a formula, formal formula in the theory T, which contains piano arithmetic, so we will be doing everything in piano arithmetic, as self-referring sentences, I am not probable in theory T. So we have to make that sentence a formula of our little piano arithmetic. And for the second theorem, one needs to translate a sentence, I am consistent. That would be I am consistent, and this A is a sentence, I am not probable. So this sentence A, which with Gödel found, means I am not probable in the theory T. And for second, for inconsistency, you have that I am consistent. So they are called self-referring sentences. The assumption in both theorems that T contains arithmetic means usually it contains piano arithmetic, or even sub-theory of RR, Robinson system. If we wanted, Robinson show, as I told you, that all this Gödel argument can be done in his Robinson system. So in the case of the final product of such translation must be a sentence A or sentence consistent T of the language, and usually the language is our language of piano arithmetic. That this translation process, and that is the whole genius of Gödel, into the language of the formal system containing arithmetic is called arithmetization and encoding, or just encoding. So you talk about arithmetization of our language, or encoding. And we define the notion of arithmetization. In general, arithmetization of a theory T is one function from the set of symbols of the language and expressions, formulas, and finite sentences, proofs. What is a formal proof? Formal proof is a finite sequence of formulas. So everything, arithmetization is one function which takes the symbols of the language, formulas, finite sequences, it means proofs, into the set of positive integers. So everything is as natural number. The function G must, of course, satisfy certain condition, must be effectively computable. There is effective procedure that determines whether any given procedure that determines whether any given positive integer n is in the range of G or n is not in the range of G. The procedure finds the object for which G x equal n. And arithmetization was originally devised by Gödel in 1931 in order to arithmetize the piano arithmetic and encode the whole arithmetization process in this our little piano arithmetic little language with 9 axioms in order to formulate and prove the incompleteness theorem. Functions and relations whose arguments and values are natural numbers are called number-theoretic functions and relations. In order to arithmetize and encode in a formal system, we have to associate numbers with symbols of the language, associate numbers with expression formulas, and with sequences of expressions of the language. It means that would be the proofs. This arithmetization of basic syntax and encoding, this is arithmetization of basic syntax and encoding of the syntax of the system. Now, we replace assertions about the system by number-theoretic statements and express these number-theoretic statements within this formal system itself. And that is arithmetization and encoding of the system. And we want number-theoretic functions to be representable. So the next is representable in piano arithmetic. It means we want the predicate to be expressible in piano arithmetic. It means their characteristic function are representable. Predicates are representable by characteristic functions. And the study of representability of function in piano arithmetic leads to the class of number-theoretic function, then in turn can be of great importance in mathematical logic, namely primitive, recursive, and recursive function. So Gödel, to do it all, he invented what we now have the whole field of mathematics of primitive, recursive, and recursive functions, and so on. So their definition and study in a form of recursion theory is an important field in mathematics and computer science, which developed out of the Gödel proof of the incompleteness theorem. 20 years old. So we prove that the class of recursive functions is identical with the class of functions representable in piano arithmetic. You can imagine that there's like this little formula in that, big formula in that piano arithmetic. So, and we prove that every recursive function is representable in piano arithmetic, and every function representable in piano arithmetic is recursive. And the representability of primitive recursive and recursive function in a formal system in general, and piano arithmetic in particular, plays crucial role in a coding process and consequently in the proof of Gödel theorem. And the details of arithmetization and encoding are complicated and 50 pages, 60 pages, and fascinating, and it's out of scope here. And again, I recommend for really, there's plenty of books which explain that and so on, but really for the beautiful formal way, I recommend Mendelssohn book. So, principle for encoding. We assume at this moment that T is some fixed but unspecified consistent formal theorem. We also assume that encoding is done in some fixed theory S, and that theory T contains S. It means the language of T is an extension of the language of S, and everything which you prove in S you can prove in T, because fat things S and fat things T is all formulas provable in S are formulas provable in T. So that, I remind you now that fat T and fat S are everything which is probable, because we are all in probability, we are all in syntax. There is no, we don't touch. So moreover, we assume, of course, because we need this Peano arithmetic, and in the Gödel theory, the theory must contain Peano arithmetic. The theories T and S contain constants, only numerals. So numbers. They are the only constants in those theories. And T contains infinitely countably many functional and predicate symbols. And usually S sub-theory is taken to be formal theory of arithmetic. But sometimes S can be weak set theory, so usually it's formal because theory of arithmetic, for example, Peano arithmetic. But it can be weaker set theory, but whatever it is, it always contains numerals. And we also assume that theories T and S are such that they follow our principle of encoding. And the mechanics condition details of encoding for T and S being for T and S being Peano arithmetic, or its sub-theory, for example, Robinson, are presented again beautifully in Mendelssohn's book. Smorinsky approach we discuss now covers a larger class of formal theories and uses more general modern approach. And again, I recommend Smorinsky chapter. It's really, really beautiful. So first, how we do it? First, we encode the syntax of the T in S. Think about Peano arithmetic. Since encoding takes place in S, we assume it has a sufficient supply of constant. It means we have countably infinite numerals and closed terms to be used as codes. And we assign for each formula of the language of T a closed term, which is called the code of A. So we have code of A. Now, if A is a formula with free variable x, the code is, we denote the code, this is the code of A. It's a closed term encoding the formula with x viewed as a syntactic object and not as parameter. And we do it recursively. First, we assign codes, unique closed terms in S, to each basic syntactic objects, as we said, elements of the alphabet of the language of T. And terms and formulas are finite sequences of the basic syntactic object, and derivation, formal proofs, are also finite sequences of formulas. So it means that as we're able to encode and manipulate finite sequences. This S means that S have to be able to encode and manipulate finite sequences. So in the next recursive step, we use such encoding. We use for such encoding a primitive recursive functions and relations. So to encode, you have certain functions, and then there's a class of functions which correspond to primitive recursive functions. And we assume S admits representation of the primitive recursive function, the relation, and we finish encoding the syntax. Now, S will also have a certain important function symbols, and we have to be able to encode them. So it must contain special functional symbols. What? Negation, implication, conjunction, disjunction, corresponding to logical connectives and quantifiers. And such that for all formulas of the language of T, in S, piano arithmetic, we can put negation of the code for A. So this is our function, which is the code of the formula negation of A. Implication AB is implication of the code of A and B, etc. So we keep going. There's also very important operation, which is substitution. So operation of substitution of variable x in the formula by a term, right, is very important. So S must always have a functional symbol substitution. And we must have, so this is a code for x, and that is a term code for t, and we must have probable that substitution is, you see here, you substituted term t, and that corresponds the code of the at when you substituted for t for x, and that refers to the code. And then you have iteration of substitutions and so on. So finally, we also encode derivation, and we do it. You must have a binary relation proof or probability for closed terms. We use the closed terms. So we say that in S prov binary relation in T, T1, T2, if and only if T1 is a code of derivation in T of the formula with the code T2. And we read X prov Txy as X proves Y in T, or X has a proof in T. So now I have a special formula, everything is encoded. And it follows that for some closed term, A has a proof in T if and only if that is exactly what this formula said, that A has a proof in T, and everything is encoded in our S. You can think about S as piano arithmetic. And now we define a probability. So, and that was all Gödel did. We define predicate asserting probability, which is there is a proof in T. That means PRTY, it means there is X, that Y is a proof of X in T. So the encoding can be carried out in such a way that we have, and that is Zmoriński, which he brought the whole apparatus to that, and that was proved by Hilbert and Bernays in, you see, they got together, even if he was developing intuitionistic logic in 1939. So, and here they are important because three conditions, and they are essential to prove Gödel's theorem. And I will use those conditions, the derivability conditions, D1, D2, D3, to prove the Gödel theorem. I should have written here. Now I can erase this a little bit, because if I talk about derivability conditions, we will, if I need it. So now I want to have, I don't need it anymore. Right? So this is important. Those derivability conditions are the key for the proof of Gödel theorem. Proof. So first, there is a lemma, which is called diagonalization lemma. It also is called fixed point theorem. And the names are used interchangeably. And the first name was historically older and important, and fixed point theorem is used, it started to be used in computer science, so it became fixed point theorem. So Mendelssohn believed that the central idea first was explicitly mentioned in Carnap, who pointed 34 that the result was implicit in the work of Gödel. Gödel did it all, but he didn't. Carnap said he really, when he was doing it, used that lemma. And Gödel was not aware of Carnap work until 37. And the name diagonalization lemma is used in main argument in the proof, and it has some resemblance to the diagonal argument used by Cantor in 1892. So that's why you have diagonalization principle, a diagonalization lemma, and in computer science it's called fixed point theorem. Okay, in mathematics, the fixed point theorem is a name of a theorem saying that a function f under some conditions will have a fixed point. It means a point where fx equals x, so that's why. And diagonalization lemma says that any formula A of the language of the theory with one free variable, there is a sentence, closed formula, such that the formula B closed if and only if that A, and here you have the code for B, is provable in T. So that is like fx equal x. You see, you can think that this is fx equal x. And intuitively, the diagonalization lemma and sentence B such that holds is called self-referential sentence saying B has a property A. The sentence B can be viewed as a fixed point of operation assigning each formula A to the sentence A code of B, and that's why it's called fixed point theorem. And here's the diagonalization lemma, that if you have T and S a theory, as we define them, and AX is any formula of the language T, and X is the only one free variable in A, then there is a sentence. You see, there is a sentence, so that's why you can see what it means. We'll use this lemma to have the self-referential sentence in Gödel theorem. So there is a sentence such that you have B is if and only if A on the code of B. So there is like language, let's skip that. And there's a proof. I am leaving you to go through this proof step by step. Short proof. It's such a beautiful proof. And the formula is, you see the substitution, Cx is if and only if X is substitution, be diagonalized, you see, be the diagonalization of Ax. And then we get the proof. And here we have first incompleteness theorem. Let T and S be our theory. Then there is a certain G of the language such that G does not have a proof in the theory, and under additional assumption, negation also does not have. We apply diagonalization lemma to a formula Ax being not proof into X. When this is the PRTX is defined, there is a proof Y, there is Y, that Y is a proof of Y. So it means prof TYX reads Y is the proof of X in T. And that sentence is called the Gödel self-referring sentence of Gödel. That's why we use G. So we get that there is a sentence, G, which says which says that in S you can prove that sentence. So we have assumed about theories T and S that T is consistent, and S is all probable things in S are probable in S. So we also have that in T, because we did it for S. In T, you can also have that that Gödel that Gödel statement with G is a Gödel sentence are probable. And now we conduct the proof that T is not in G by contradiction. Assume that I can prove Gödel sentence in T, and by contradiction D1, proof of A in T implies this. If you take the A equal G, we get that proof in TG implies proof of probability of the code of G, probability code for G. So the assumption that G is in T, we get that in S we have probability, because by assumption that S is subset of T, we get that we get that this, right? But we have assumption that everything probable in S is probable with T. I get that that is probable with T. So this assumption is already proof, so that contradicts that consistency of T. And now we have to prove that under additional assumption. So additional assumption is strengthening of the converse implication of D1. So it means this additional assumption, I assume that this in T, PRT code of G implies G is probable T, and then I want to prove that in this, under this assumption, I will have that T does not prove not G. So assume that T prove G. So we have double negation of PRTG. We also have that T proves the G. And by additional assumption, that would imply that it proves G, what contradicts the consistency of T, end of the proof. Now observe that the sentence G is equivalent in T to an assertion that G is improbable, right? Because by definition we say G says I am not probable in T. Hence we prove second incompleteness theorem. Hence our second incompleteness theorem provides a strict mathematical formalization of intuitively stated version, which says there is a sentence A of the language T which asserts its own unprobability, because the sentence G is I am not probable. So and we call this G this is the shortest proof I could find of Gödel theorem. Of course, with various three conditions. But so second incompleteness theorem. Now we have still our TNS, and now our contradiction be a sentence, not PRT-C, where C is any contradictory, so it's not probable, and C is any contradictory statement. So then we cannot prove in T that cond T. So let's and what we take? We take Gödel sentence. By first incompleteness theorem, we prove that cond is if and only G, contradiction T is if and only G, and we use to prove that T does not prove contradiction. And it's a little bit more moves. So assume now that we already proved that property. We conduct the proof of that by contradiction. Assume that I can prove this. By this, we have that T prove con if and only G. So by the assumption, we get that it proves T, which contradicts the first incompleteness theorem. To complete the proof, we have to prove this star property. The proof of that property star uses some logic facts, which are, you can figure it out. But I listed them at the end of the proof. Logic 1, 2, 3, 4 propositional beautiful properties. So by logic 1, we get this. And now, and we prove that implication. We prove this implication by definition of contradiction T. We get that formula is a contradiction. We have that C implies G is a predicate tautology. So it is probable in T. And by condition D1, we get that property. And now, by D3, for A equal PRT quote of C, we get this property star. And then by logic 2, we get double star property. And by logic 3 and those two, we get this property. And apply logic 4. You can figure out those logic by yourself, but I listed those logic 1, 2, 3, and 4. We get the fact that triple star. And now we know that by first incompleteness theorem, S proves that formula. We put this triple star and the property above together, and we get that G, in S you prove that formula, in S you prove this formula, and now we apply logic 4 to the above, and we get that in S we could prove the implication G implies negation of PRT. By C is the definition contradiction, so we have proved that G implies the contradiction, so we prove that in T, G implies contradiction T. And the second, we have to prove the inverse implication. Contradiction implies G. It means that that implication, and here is a concise proof, and we leave to the reader as an exercise to write detailed version as I developed with those logic 1, 2, 3 for that part of the proof. And the proof goes by derivability condition D2 for A equal G. You have that condition by this property implies this by D1 and D3. Since you have proof in S that formula, and that yields that in S you prove that formula by D1 and D3 and logic properties for you to develop. In a way, I developed this logic 1, 2, 3, 4, and in terms that implies this formula again by D1, D3, and some other logic properties, so that needs some. And then you can apply that logic 4, and we get that S proves this formula, which is really contradiction T implies G. And because we assume that all theorems of S are theorems of T, we get also that in T, contradiction implies D, which ends the proof. So, observations. We prove a part of the proof of the second incompleteness theorem, the equivalence, that in T, contradiction is if and only G, which says that self-referential Gödel sentence asserts its own unprovability. That is the sentence, self-referential Gödel sentence which asserts its own unprobability is equivalent to a sentence asserting consistency. Hence, the sentence G is unique up to probable equivalences, contradiction T if and only G, and we can say that G is the sentence that asserts its own probability. Whew, that was, and then we can have a concept of omega consistencies and put it in the first incompleteness theorem and so on. So informally, omega inconsistent, we defined what does it means omega consistencies, and we get the statement with omega consistencies for the Gödel of the Gödel theorem. And here I listed the logical four logical properties, and so in the second part of the proof of incompleteness, I ask you to develop that kind of reasoning to see how you get the short, to make the short proof a long proof using that. And the last thing, we have formalized completeness theorem, which you can just I want to mention. Hilbert-Burness completeness theorem, which says that if U be any theory with primitive recursive set of axioms, where the set TRM of formulas such that piano on consistency of U, one can prove that this set defines a model M of U. And piano plus consistency U proves that formula. So, and then you have all modern development of following the classical Gödel incompleteness theorem. And you can have use, yeah, so that's a little bit of discussion of more. I brought this to your attention because Gödel chose a self-referring sentence, a syntactic sentence. I do not have a proof. He did not want, and saw difficulties with, the use of sentence involving semantics. You see, I do not have a proof. We use that. I am not true. The new proofs use exactly this semantic statement, and that's why they are called modal theoretic proofs. And Dana Scott was first to observe that one can give modal theoretic proof of first incompleteness theorem. Dana Scott, I brought Dana Scott because for computer science, everybody knows Dana Scott. So first incompleteness theorem by Dana Scott is let PA be piano arithmetic. There is a sentence G of piano such that does not prove piano arithmetic does not prove G, and piano arithmetic does not prove negation of G, and this it goes like this, that assume that piano arithmetic is complete. Since PA is true, PA proves consistency PA, and then we can apply Hilbert-Burness completeness theorem to the formula TRM, which gives truth definition of the model of piano arithmetic. And now we choose as G that statement. So that is what, and now the G, such defined, asserts that I am not true. So that's why it's model theoretic version of Gödel theorem, which Gödel didn't want to go into. And that, and then you can go second incompleteness theorem, and you have another proof of second model theoretic proof of second incompleteness theorem. So thank you very much. We are done with we are done.